Hi, so we're finally ready to talk about the code for Dijkstra's shortest path first algorithm. So here is again the pseudocode for Dijkstra. We're gonna implement this almost verbatim, but not quite. One small change that we're gonna make is or it wasn't obvious from the pseudocode is what kind of data structure can we use for partial path? Right, take a look at this. The operation that we do the most is to insert the partial vertex into partial path, and then we remove from the partial path the vertex with the shortest distance. So what kind of data structure does that call for? And hopefully it's somewhat obvious that it really calls for a min heap, right? Because we want the shortest, we want the vertex with the smallest cost. So now we could use our min heap, which would work fine, but since we know Python has a heap queue, and I kind of like to explore using it, so that's what we'll go for. Now, so heap queue itself is not a data structure. It's just a functions that uses the Python's list as a binary min heap. So you can look at the documentation here, but we really just need three functions from it. So the first thing is heapify, given a list. So it will transform the list into a heap, and it says it can do it in linear time, which it's kind of what we know it's possible. And then the next two things is obviously we need to put something into the heap and then get the minimum or extract the minimum from the heap. So that's heap push and then heap pop. And obviously both of these functions, it would kind of heapify the list to maintain the heap invariant. So if I've already typed out the code here, I'll just go through all the relevant lines here. So the first thing is we need this nested class path that holds the Dijkstra specific information for a vertex. And those information is two pieces of information. One is the total cost of the path, and then the second piece of information is the previous vertex in the path, right? And we initialize the total cost to infinity. This is how you initialize the largest floating number in Python. And then for the previous vertex, obviously, um, we don't know yet, right? So that is set to none. Now I put this inside a reset function or reset method, and that is because every time we want to run Dijkstra, we want to reset this information right at the beginning. Otherwise, because they these information live with the vertex, and the vertex persist in the graph. If we don't reset these information, then if Dijkstra is run the second or the third time, um, things could go really wrong. Okay, and that's really that. And then also for the vertex class itself, remember we want to put the vertices in the min heap, and then we want to remove the vertex with the minimum um, path cost. And so therefore, we override the dunder LT method so that it will compare the path cost uh, when the min heap needs to remove the minimum. And this is the actual Dijkstra implementation. I actually called it SPF, shortest path first, in case we're not using Dijkstra, but most likely we are. Anyway, so the first thing we do, as usual, we look up the source. Well, we are given the source and the destination. Um, and we want to make sure, the source and the destination vertices, they do indeed exist inside our dictionary, and that's what we do. And then, like we said, we would like to reset all the Dijkstra specific info in all the vertices. I'll show how this works in a little bit. And then the next thing is, yes, we want to keep all the partial paths in, well, partial paths, and we will bootstrap the partial paths with the source. Like, remember, we did this in our demo, and when we bootstrap the source, obviously, from the source to get to the source, the cost will be 0, and the previous path, a previous vertex in that path is the source itself. And now the loop, this just will loop as long as there is something in the min heap of all the partial paths. First thing we do is we remove the vertex with the minimum cost. And then for that min vertex, we look at all of its outgoing edges. So and each of these edge has a destination, and we'll calculate the new cost of reaching that destination through the current min vertex plus the edge that connects the min vertex to the destination vertex. So that's what this addition is doing here. And then if the new cost is less than the existing cost that's known, so remember this could be a number if there's already a path that is found, or it could be infinity. So either way, it's fine. So if the new cost is cheaper, then we would have to update that destination's path so that it goes through the current path with the new cost. Now, finally, remember the last step, the pseudocode actually calls for insert this destination vertex into the partial paths min queue. Right now, there are two situations or two cases that we have to handle. First is if that vertex is already in the partial path. In that case, its cost has been updated, so most likely the min heap invariant has been violated. So in that case, we will just have to heapify the min heap to make sure it's still a min heap. If the destination, if that vertex is not already in the partial paths, it's the first time that we actually find a path to that destination, then we can simply do a insert of that vertex into the partial paths. And then that's it. It loops through this over and over until, yeah, we are done with all the reachable vertices. And then finally, we'll build a return path that we can return to the client. Next, let's look at what these two helper methods do. First, let's look at reset path, which is fairly straightforward. Like I said, we want to be able to run Dijkstra over and over. So we just go through all the vertices. Remember, vertices is a dictionary, so to actually go through the vertices vertex objects, then we have to get the values from the dictionary, and for each one of them, we reset the path. Now, as to how to retrieve the result of running Dijkstra, there are several choices. Now, the approach used in the readings is simply to print them out, but as I said many times, printing out is only good when humans want to look at it. It's not good if we actually want to write test so that we can test the return or the result of Dijkstra, or if we want to take that result of running Dijkstra and pass it on to other functions or methods for further processing. So what I chose to do is that I'll choose we're going to return a tuple of the path and the total cost. And what that path is just a list of all the vertex IDs along that path. So what I'm showing here is well, given the source and the destination, right? And we'll start from the destination. Remember, in order to figure out the whole path, we start with the destination and we go backwards, tracing through the from vertex. So anyway, we start at the destination. We put the destination in a path, and then as long as we haven't got to the source, and as long as there is a from vertex that we can move backward towards, we'll insert the from vertex into the path. Now I put it rather than using append, I insert it in the front of the list so that I don't have to do a reverse at the end, because again, this is going backwards. Anyway, so when we're done, we'll return the IDs for all the vertices in this path, along with, again, just the total cost of the path. Okay, now that we have an implementation, we do what else? Testing. The first thing is I'm going to use this graph that I use for the Dijkstra demo. I'm going to use it multiple times, so I'm going to create this graph in the setup method of the test, and remember it as self.graph1. And I also make a small change such that I actually added an extra vertex, Z, that is totally disconnected from anything else. I just want to make sure it works in that case. So I've already typed all of these things up, obviously. Now, as for the test itself, there's a couple kind of corner edge cases that we really should always test. So the very first thing is, what if we want to find the shortest path between the same vertex, right, from S to S? So we would expect, in that case, that it returns the path with just the vertex itself at a cost of 0. Right? And then another test that if we try to go to a destination vertex that's just disconnected from the rest of the vertices. So from S to Z, Z is totally disconnected. So the path should consist of just Z itself, but the cost would be infinite, which kind of signals that Z is unreachable from S. And we also should do the same thing, but this time put Z as a source rather than the destination. Now, we might choose to, if it's Z is unreachable, we might want to say the path would be empty, but that kind of depends on, again, the application requirement. And finally, the real actual big test itself is, as in our demo, we want to find the shortest path between S and V. And as we already figured out, the path should be SXUV and at a cost of 9. And that's what we test here. And then I want to make sure it can be run the second time. So I run it the second time with a slightly different pair of source and destination, and that's what we expect. So so we can run this, and wait, I can show you that it runs. It took me a bit of time to get all the bugs ironed out, but all the tests passed. And so I think it's, now that I've shown you how the code works, it's your turn to kind of test the code. And also, since you've previously gone through this exercise by hand, then you can kind of reconcile that result with the result from running the code, and hopefully the two agree with each other.